In this video, I introduce a maximum likelihood estimate and a maximum posteriori estimate. Bayesian theory is the foundation of AI and machine learning, but its idea is simple. However, its application is not straightforward. Bayesian theory describes a relationship between prior, likelihood, potential function, and posteriori. Here, A is a hypothesis and B is evidence. Bayesian theory is used to solve AI and machine learning problems using two methods. One is a maximum likelihood estimate, another one is a maximum posteriori estimate. First, let's see how can we use maximum likelihood estimate to solve the reinforcement learning problem to find the optimal policy. First, we need to know what's the prior, because we don't have much information about the prior. So we just randomly pick up this theta and get the initial, use as an initial distribution. Once we have this initial model parameter distribution, and then we use state as an input to the model, and the model predicts the probability of action A. Once we have this prediction, then we can compare with the ground truth through the gradient descent method to find the gradient of the loss function, and then use the gradient to update these model parameters. After we update these model parameters, that means we already improved this prior. Use this in prior, that means we already increase the model confidence. Use the new model parameters. Then we can update, calculate, predict the probability of action again. And then we update this model parameter theta again until we reach the convergent. Once we get the convergent of the model parameters, then use a new state as an input to the model. The model can accurately predict the probability of the action and receive the maximum reward. That's for the maximum likelihood estimate. Next, let's see how can we use the maximum posteriori estimate to estimate the probability of this A for given evidence B. For example, if this training data set is small, so we can use the regression method to find the model parameters, and use the model parameters for any given evidence. We can use the model to find the variable A. However, for the practical applications, the training data is big. We cannot directly use the simply use the regression method to find the model parameters. So that's why we still need the deep neural network as the maximum posteriori estimate model. For example, let's see how can we use the maximum posteriori estimate model to in the inverse reinforcement learning, find the real-world function from the expert trajectory. So you just pick up a state from the expert trajectory as the input to the network. We need to use the maximum posteriori estimate model to estimate the real-world function. Similarly, because we don't know much information about this Q initially, so we need to randomly pick up a theta distribution as the initial theta distribution to estimate this real-world R. However, this is R, we don't have a ground truth to update these model parameters. However, we can use this real-world function in the reinforcement learning to find the policy pi. And then we use as a policy pi to generate a trajectory, as a predicted trajectory. And then we compare to the export trajectory to find the gradient of the loss function. And then we use the gradient to update the model parameters. Then we step by step until we reach the convergent model parameter theta. Once we have a convergent theta distribution, then we can get a state from trajectory as an input to the model, and the model can estimate the reward function. That's the idea. How can we use the maximum posteriori estimate model in the inverse reinforcement learning to estimate the reward function from the export trajectory. For more detail, please check with this reference. Thank you. Bye.